What is weight? You've probably heard throughout your schooling that mass is a property of matter. Okay, so it's inherent to matter. No matter what's going on with that matter, mass is a property of that matter. So it doesn't depend on what's happening to the matter. Weight is often thought of as just a type of mass, or a way of measuring mass, or something like that. And that's not a bad interpretation, it's not a bad intuition, because generally when we weigh something, what we do is we put this object on a scale. Here's my object, and that scale feels how heavy this object is. This object pushes down on the scale because the Earth is pulling down with a force equal to mg. And so since m is the mass of the object, g is the gravitational acceleration, together the product is the force of gravity, then the scale pushing back up on that that rock, or that mass there, tells us how big mg is. And so we say, oh, well, weight, mass, kind of the same thing. It's just weight technically is a newton, it's a force, but it's pretty much proportional to mass. And in fact, so much so that our scales that we'd stand on in our bathroom scales say kilograms, or they say pounds, and that is a measure of mass. Okay? So the distinction we need to make clear is that that's not true, is that mass is a property of matter. Weight is not just mg in all times and all places. It's often mg, but it's not always. So first thing is weight and mass are not equal. Mass is units of kilograms in SI units. Weight has units of newtons. Okay. If in our standard case, if we say our standard weight, we sometimes can say that mg equals our weight in our standard case. And I have to clarify what standard means. We're going to do a couple examples to emphasize that. Okay. So if I were to do a free body diagram of this situation right here on the rock, so my rock is my object of interest. I look at it and I see force of gravity is pulling down on it, and I see that there is an upward normal force by the scale. So doing that, I get upward normal force, downward force of gravity, and this upward normal force. And because it's in equilibrium, I know that F net is 0. And therefore the upward normal force must equal the downward gravitational force. And I can say N equals mg. So from this, I can shoot to N equals mg. Okay. Now what I'm going to say is that what is the weight at all times would be that normal force that's holding something up. Okay. So it's whenever gravity is pulling something down, whatever is keeping it from going down, or whatever holding it up, is the weight. So in this case, the normal force equals the weight. Okay. So in this case, that's mg, and we can just divide our answer by g to get a scale reading that's in kilograms, which is what we'd have in our bathroom. But what about this case? What if I have a scale, and I'm standing on it, and I'm reading my weight? Well, in my bathroom, I would read my mg, okay, because I'm not accelerating. The net force is 0, and so the upward normal force, which is the scale reading, which is the weight, is equal to mg downward. What if I am on a pedestal that is accelerating downward? Okay, this might be in an elevator. I'm in an elevator, just got on at the 3rd floor, and now I've pressed the button for the 1st floor, and for the first few moments the elevator is accelerating downward because it's at rest to start on the 3rd floor, and now has to get up to some certain speed to get down to the 1st floor. So I'm accelerating downward. Well, then my free body diagram still has just that upward normal force, but my gravitational force, okay, well, I need to say that a little bit differently. My gravitational force is the same. It's just mg. That doesn't change. But my normal force must have gotten smaller, because now the net force must be downward, because my acceleration is downward. Okay? So by doing my free body diagram and equating forces and recognizing that the net force indicates the direction of acceleration, a non-zero acceleration means, in this case, my normal force is less than mg. So my weight is less than mg in this case. Okay. Now let's take it to an extreme level. This might be a little bit scary. I hope no one's been in this situation, so this brings back some traumatic memory. But what if this pedestal breaks and falls out from underneath me? So now I'm sitting in the air, still standing on that scale, but we are now falling. So we are accelerating downward, but we have a specific acceleration. Our acceleration is equal to g downward. I guess I'll have the vector sign indicating downward. Okay, but it's of size g. Okay, so if I think about that and use Newton's second law, when I look at the force acting on me, I'm touching this scale. Okay, so there's a normal force and there's a gravitational force, and so I'm going to say that I've got N, which is my upward force, minus mg, which is my downward force, so it's just like this. N minus mg is going to equal ma. Okay, now all this is in the y direction, so I'm going to be careful to put that subscript, ay. Okay, but I already know that that's equal to mg downward. I didn't leave room for a minus sign. Okay, so there's negative mg. Alright, so I have n, add this over to the other side, equals mg minus this minus mg here. mg equals 0. My normal force is 0. Okay, so I am falling at a rate of g. My gravitational force is mg, so that equals ma, which is now mg by Newton's second law, which means n has to be 0. Okay, I could, in this case, as I'm falling, pick my feet up, and it would be no different. Okay, the scale would keep falling at g, I'd be falling at g, and I could pick my feet up, and there would be no difference. I have feet down, but there's no normal force. I am not applying any pressure to that scale. So these three cases help to clarify what weight is. It is not mass. It's a different unit technically, though our scales can be calibrated to convert a true weight, mg, into a kilogram by just dividing by g. That's how they're calibrated. But we need to be more careful to recognize that it comes from applying Newton's second law to the system that's being weighed. And in our standard case, we assume that that object is not accelerating. Therefore, F net equals 0, and the normal force equals mg, and the normal force is away. But as we see in these two cases, if the acceleration is non-zero, then our normal force does not equal mg, and our weight therefore differs from mg. In the extreme case of weightlessness, our normal force is 0 because we are falling with an acceleration of g, and therefore our weight is 0. The normal force has gone to 0.